All right, buckle up, everybody, because today we're diving deep into some seriously cool tech atomic operations in PCIe Gen 5.
Ooh.
You sent over some seriously dense documents on this.
Yeah, they're pretty intense.
So let's unpack it.
Yeah, break it down.
What's got you so intrigued? I know that PCIe is like the data superhighway inside our computers.
Right.
Gen 5 being the latest and greatest and fastest version.
It's incredible.
We're talking 32 gigatransfers per second per lane.
Per lane, yeah.
That's insane.
It's crazy.
That's got to be impacting everything from graphics cards to SSDs, right?
Absolutely. It's a massive leap forward in bandwidth, but what's really fascinating about Gen 5 is how it handles all that speed with atomic operation transactions. Support.
Okay, atomic operations.
Yeah.
Sounds kind of intense.
It is.
Are we talking nuclear fission here?
Not quite.
Break it down for me.
Okay.
Why should I, someone already knee-deep in PCIe docs, care about this?
Think of atomic operations like this. Imagine you and a friend both trying to grab the last concert ticket online.
Okay.
Things could get messy, right?
Oh, yeah.
Atomic operations assure that complex actions in memory happen as a single unbreakable unit. It's like guaranteeing only one of you can snag that ticket, no matter how fast you both click.
So it's all about avoiding digital brawls over data.
Exactly.
I like it.
Yeah.
But are there other technologies doing this too? Like, what about CXL?
Mm-hmm.
Isn't that supposed to be the next big thing in interconnects?
Good point. CXL also leverages atomic operations, but it has a different focus.
Okay.
PCIe Gen 5 is like a Swiss Army knife for concurrent memory access,
Uh-huh.
while CXL is more specialized for CPU to accelerator communication, like making sure your CPU and GPU play nicely together.
So CXL is more about teamwork, while PCIe Gen 5 is about making sure nobody trips over each other on the dance floor.
Exactly. Now, within PCIe Gen 5, there are three main types of atomic operations.
Okay.
Fetch add, swap, and CAS.
All right, hit me with the first one, fetch add.
Okay.
What's that all about?
Imagine a website tracking visitor count. Fetch add lets you atomically add to that counter while simultaneously retrieving the original value. It's like grabbing a number, adding to it, and knowing exactly what it was before, all in one swift move.
So if two people hit the website at the exact same time,
Right.
fetch add makes sure the count doesn't get messed up.
Precisely. That's why it's super useful for synchronization and managing shared resources.
Okay.
Now, swap is a bit similar.
Hold on.
Yeah.
Wouldn't swapping values like that cause chaos if multiple things are trying to access the same spot?
That's where the atomic part comes in.
Right.
It ensures the swap happens as a single unbreakable action,
Okay.
preventing any data corruption.
Gotcha.
Imagine it like a perfectly choreographed switcheroo in memory.
Okay, I'm starting to see why this is a big deal.
It's pretty cool.
But what about that third type you mentioned, CAS?
CAS stands for compare and swap.
Okay.
It's a bit more intricate.
Okay.
It checks if the data at a memory location matches an expected value.
Mm-hmm.
If they match, it swaps on a new value.
Okay.
If not, it does nothing.
Interesting.
It's like a conditional swap, adding an extra layer of safety.
So CAS is like a bouncer at the club,
Uh-huh.
making sure only the right data gets in?
You got it.
Okay, these atomic operations sound awesome.
Yeah.
But how do they actually work their magic inside my computer?
It's complicated.
I mean, we're talking about data sipping around at insane speeds.
Gen 5 had to get clever with how these signals travel to avoid errors.
Okay.
Think of it like super efficient traffic management for data.
Okay.
Making sure everything arrives at its destination safely and on time.
All right, but you can't just wave a magic wand and make data behave.
Nope.
What are some of the engineering hurdles involved in making this all work seamlessly?
Well, for one, there's the challenge of increased channel loss.
Uh-huh.
Remember, PCIe Gen 5 doubles the data rate,
Right.
meaning signals travel much faster.
Got it.
And as they zip along, they can lose strength, like a game of telephone.
So the faster the data travels,
Yeah.
the more likely it is to be garbled along the way.
Pretty much.
It sounds like a recipe for disaster.
Exactly. To combat that, designers have to be incredibly meticulous about minimizing signal loss,
Okay.
carefully considering everything from the materials used to how the data lanes are physically laid out.
So it's a constant battle against the laws of physics.
It is.
I bet that makes designing the controllers a real headache, too.
You're absolutely right.
Yeah.
PCIe 5.0 controllers need to be more sophisticated to handle all this,
Right.
which can impact power consumption and physical space on the chip.
Okay.
It's a delicate balancing act between performance, efficiency, and size.
Kind of like trying to cram a supercomputer into a matchbox.
Pretty much.
Anything else that keeps the engineers up at night?
Another big one is ensuring smooth integration between the PHY and the controller.
Okay, the PHY.
Yeah, the PHY handles the physical data transmission,
Okay.
while the controller manages the logic.
Gotcha.
They need to be perfectly in sync,
Okay.
like a conductor and an orchestra, for data to flow efficiently.
So if the PHY is playing Beethoven and the controller's doing jazz, things are going to get messy.
Exactly. And this requires careful consideration of things like the PCIe interface.
Oh, the PCIe interface?
Yeah, that's the connection between the physical and logical components.
Okay.
As well as data path width.
Okay, data path width.
Which determines how much data can be transmitted at once.
Got it.
Yeah.
It sounds like there are a lot of moving parts to keep in harmony.
A lot of them.
Now, you mentioned earlier that older PCIe versions didn't have dedicated hardware support for atomic operations.
Right.
How did they manage without it?
They relied on software-assisted mechanisms like locked memory reads and writes.
Huh, okay.
Imagine trying to collaborate on a document with a colleague, but you have to take turns editing because only one person can lock the file at a time.
So it was like the digital version of those old track changes features.
Exactly.
Slow and clunky.
Yeah.
And that's where Gen 5 shines.
It really does.
By directly integrating atomic operations into the hardware.
Right.
They eliminate those bottlenecks.
Exactly.
It's like everyone being able to edit the document simultaneously.
Yeah.
With changes merging seamlessly.
It's amazing.
So no more digital traffic jams?
No more.
That's a huge win.
It is.
Now, I can't resist a good comparison.
All right, let's do it.
We talked about CXL earlier. How does PCIe Gen 5 with atomic operations compare to CXL in terms of performance and use cases?
It's an interesting question.
Yeah.
Both technologies offer significant performance improvements, but they have different strengths.
Okay.
Remember that Swiss Army knife analogy?
Oh, yeah.
PCIe Gen 5 is versatile, offering a broad range of benefits, including atomic operations.
Right.
CXL, on the other hand, is laser-focused on coherent memory sharing.
Gotcha.
Specifically between CPUs and accelerators like GPUs.
So if PCIe Gen 5 is a multi-tool, CXL is like a high-powered surgical instrument.
Exactly.
Each with its own specific purpose.
Yeah, think of it this way.
Okay.
PCIe Gen 5 is great for general-purpose memory access and synchronization across a wide variety of devices.
Okay.
CXL excels at connecting CPUs to accelerators, enabling them to share memory as if it were a single unified space.
Okay, that makes sense.
Yeah.
It's not about one being better, but rather each having its sweet spot.
Exactly.
Now, as we're talking about all this, there's a quote from the research you sent that really stood out to me.
Oh, yeah.
The use of legacy lock operations on PCIe devices is limited and can lead to performance penalties, highlighting the need for dedicated atomic operation support in PCIe Gen 5.
It's a good one.
What are your thoughts on that?
That quote really nails it.
Yeah.
It highlights why Gen 5 is such a game changer. It's not just an incremental upgrade.
Right.
It addresses real limitations and unlocks a whole new level of performance and efficiency.
It's like finally ditching that old dial-up modem and getting fiber optic internet.
Exactly.
Speaking of real-world impact,
yeah.
Can you give us some concrete examples of how atomic operations in PCIe Gen 5 are actually being used today?
Absolutely. One great example is lock-free queues.
Okay, lock-free queues.
Commonly used in high-performance systems to manage data flow.
Okay.
Imagine a busy airport security line with everyone funneling through a single checkpoint.
Yeah, I've been there.
That checkpoint is like a traditional lock.
Okay.
A bottleneck that slows things down.
Right.
Lock-free queues using atomic operations allow multiple people to go through security simultaneously, eliminating the bottleneck and speeding things up significantly.
So it's like having multiple security lanes operating smoothly?
Yeah.
Without any collisions or delays?
Exactly.
That's a fantastic visual.
Thanks.
What about other examples?
Let's talk about concurrent hash tables.
Okay, concurrent hash tables.
These are data structures used to store and retrieve information quickly.
Okay.
Think of a library where you can search for a book by its title.
Okay, I got you.
A traditional hash table would require each person to wait their turn to search, creating a potential bottleneck.
Okay.
But a concurrent hash table, using atomic operations, allows multiple people to search for books simultaneously without interfering with each other.
So it's like having multiple librarians all helping you find the right book at the same time?
Exactly.
No more waiting around in the digital stacks?
That's the idea.
And another example is distributed counters, which are crucial for tracking things like website visits in a distributed system.
Yeah, that's a big one.
These counters might be spread across multiple servers, and atomic operations ensure that each server updates the count accurately, even if multiple updates happen simultaneously.
Yeah, it's pretty cool.
It's like having a perfectly synchronized tally system, making sure every visit is counted no matter where it originates.
Exactly.
What other fascinating use cases are out there?
Well, atomic operations are also playing a crucial role in the world of heterogeneous computing.
Heterogeneous computing?
Yeah, for instance, RCM, AMD's open-source platform for GPU computing, utilizes atomic operations to manage communication between CPUs and GPUs. This ensures efficient and synchronized data transfers,
Gotcha.
allowing CPUs and GPUs to work together seamlessly to tackle complex computational tasks.
Wow, so atomic operations are quietly powering everything from website analytics to cutting-edge GPU computing.
They really are.
That's pretty remarkable.
It is. It really speaks to the ingenuity of engineers and their constant drive to push the boundaries of what's possible with technology.
It seems like we've only scratched the surface of what atomic operations can do.
Yeah, just the tip of the iceberg.
It's amazing how these tiny behind-the-scenes mechanisms are powering such a wide range of applications.
It really is incredible.
So as we start to wrap up our deep dive,
Okay.
what are some of the key takeaways our listeners should remember about atomic operations in PCIe Gen 5?
Well, first and foremost,
Yeah.
atomic operations are a game changer for high-performance computing, distributed systems, and databases.
Okay.
They're all about making things smoother, faster, and more efficient.
It's like upgrading from a horse and buggy to a supersonic jet.
I like that analogy.
No more digital traffic jams or data collisions.
Exactly. By ensuring that complex actions in memory happen as a single, unbreakable unit,
Right.
atomic operations eliminate those race conditions and data corruption issues that plagued older PCIe generations.
Okay.
And with dedicated hardware support in Gen 5, we're seeing a whole new level of efficiency and performance.
And we've seen how that translates into tangible benefits.
Yeah, for sure.
Faster data processing,
Right.
smoother multitasking,
Absolutely.
more secure financial transactions,
Definitely.
and even advancements in areas like GPU computing.
Mm-hmm.
It's clear that atomic operations are playing a crucial role in shaping the future of computing.
There's no doubt about it.
Which brings us to a final thought-provoking question for our listeners.
Okay, hit me.
If atomic operations are already this powerful,
Yeah.
what incredible possibilities will they unlock in future PCIe generations?
That's a great question.
What new frontiers will we be able to explore when we have even faster and more sophisticated tools at our disposal?
That's a fascinating question to ponder.
Yeah.
The potential is truly vast. As we move towards exascale computing and beyond,
Right.
atomic operations will undoubtedly be instrumental in enabling us to tackle some of the most complex and challenging computational problems facing humanity.
Well, folks, it's time for us to resurface from our deep dive into atomic operations in PCIe Gen 5.
Back to the surface.
We've explored the intricate workings,
Yeah.
the real-world benefits,
Uh-huh.
and the engineering challenges behind this game-changing technology.
It's been a great deep dive.
It's clear that even though atomic operations work behind the scenes,
Right.
their impact is far-reaching and will only continue to grow.
Absolutely.
Keep those sources you send handy and explore further. There's a whole universe of knowledge waiting to be discovered.
So much to learn.
And maybe, just maybe, you'll be the one to unlock the next breakthrough in atomic operations.
I hope so.
Until next time, thanks for joining us on The Deep Dive.